For this lesson, we're going to multiply and divide radical expressions. To do so, we're going to need a couple of facts. So to start with here, if you multiply the square root of x by the square root of y, this is equivalent to the square root of x times y. So if you see a product, you can write the x and the y as a product underneath one square root. Let's see how this fact can be used in example 1. So to start with, what is the square root of 5x multiplied to these three terms? To multiply this out, I have to use the distributive property, so let's start there. Okay, this 5x under the square root gets multiplied to these three terms. So my first step will be to simply write this as the square root of 5x. I'll put a little mark here to indicate that the root stops, and then it's being multiplied by 5. So this extra 5 is actually not under the square root. If I continue, I get the square root of 5x times the square root of 5x. And then I get the square root of 5x times the square root of 2x. So nothing brand new here, this is just the distributive property. But now, let's use this fact up here to try to combine these things. Like, okay, I can't do anything here because this 5 isn't under a square root. In fact, it's customary to put the numbers that appear in the front. So I'm just going to reverse this and call it 5. And then the piece that has the variable, I'll put second, so it's 5 times the square root of 5x. But for this middle term here, according to this rule, I can take this 5x and this 5x, multiply them together, and put it underneath one square root. So this is the square root of 5x times 5x. I can do the same thing for the last term. This is the square root of 5x times 2x. All right, continuing, I think this can be simplified a little bit more because for this very first square root that we have here with the product underneath it, this is really 25 times x squared. And similarly for the last one, that's 10 times x squared. And I'm noticing here, okay, we ended up with a 25 under a square root and an x squared under a square root. Taking this property backwards, you can square root the 25 and the x squared nicely. So I'll leave again this first 5 root 5x alone, but here the square root of 25 is 5, and the square root of x squared is just x. Applying that same logic here, I have a product. I can take the square root of these two things separately. This is the square root of 10 times the square root of x squared, which is just x. If you have an exponent of 2 under a square root, it's nice that those two things just cancel to give you x. And here again, I'm writing the variable last and the number first. So after distributing the square root of 5x to the three terms and simplifying a little bit, I got this as my final answer, and this looks like it can't be simplified anymore. Let's try this again in the square root of 7 plus the square root of 2x all squared. What happens here? So for this problem, I'm going to rewrite it as the square root of 7 plus the square root of 2x times itself. That is what the square root means. It means multiply this thing by itself twice. So here, I'm again using the distributive property, but I'm doing it 2 times, where I first multiply in the square root of 7, and then as my second step, I multiply in the square root of 2x. Let's see what we get. If I multiply in the square root of 7, I get the square root of 7 times the square root of 7, plus the square root of 7 times the square root of 2x. That came from multiplying this to both terms. Let's repeat this process with the square root of 2x. I first get the square root of 2x times the square root of 7 plus the square root of 2x times the square root of 2x. So at this point, I've multiplied everything together. All right, where to go from here? Okay, let's see. Well, I'm noticing over here that this is the same thing as the square root of 7 times 7, which is 49. So again, I'm going back to this rule and I'm saying, oh, well, I can take the things under the square root and multiply them together and put it underneath one square root. So that's 7 times 7 underneath one of those. For my middle terms, I'm noticing that they're exactly the same thing, but they're written in a reverse order. Said another way, these two middle terms are the same thing as saying you have 2 square roots of 7 times the square root of 2x. There's one here, there's a second one here. That's the same thing as saying you have 2 of those things. And at the very end, again, going back to this rule, I have, this is the square root of 2x times 2x. And let's continue. All right, the square root of 49 is just 7, so really no surprise here. This square root times this square root gave us just 7. I can't do anything with the middle terms. I could write this as 1 square root, so let's try that. This is 2 times the square root of 7 times 2 is 14x. And at the very end, I get 2 times 2 is 4, and x times x is x squared. Scanning this, I can't do anything with the 7. Can't break this apart anymore. There's no perfect squares. But here, I have 4, and when I take the square root of 4, I get 2. Here I have x. When I take its x squared, and when I take its square root, I get just x. I'm going to take this one step further, where this is 7 plus 2 times the square root of 14x, but then plus 2x. So this is the final answer to this problem here. And that is it for example 1. The property that held for multiplying 2 square roots holds for dividing them, where if you're dividing 2 square roots, you can change it into 1 square root with a fraction underneath it. Let's try this rule in example 2. And let's start simple just by looking at something that has numbers in it. So this is applying this rule, but just going backwards. How can I simplify this number? Well, according to this rule, this is equivalent to the square root of 7 divided by the square root of 25. One reason you might think to do this is that, oh, well, the square root of 25 has a nice square root. The one for 7 doesn't. So to really deal with this, I have to break it up into 2 separate pieces. I can't do anything with the square root of 7. I'm just going to leave it as is. But the square root of 25 is 5. So this statement is equivalent to this one if you break it up into 2 square roots between the numerator and the denominator. And so I'll leave this as the simplified answer. I think what will be more interesting is something with some variables in it, where I'm going to take this rule, I see I have 2 separate square roots, and I'm going to change it to just 1 square root. So that is, I have the square root, and I'm going to copy down 45x cubed y squared over 6xy to the 6th. So again, I'm just taking the fraction, copying it down, and placing it under 1 square root. If I focus on what's underneath the square root, I see 6 can go into 54, x to the first can cancel into an x cubed, and this y squared can cancel into this y to the 6th. By that I mean 54 divided by 6 itself is just 9. Okay, here we have x cubed divided by x to the first. That's x to the 3 minus 1. And similarly for the y's, we have y to the 2 minus 6. I can subtract the exponents. And this really is equal to the square root of 9 times x squared y to the negative 4th. And that negative exponent on the y really means I'm dealing with a fraction. I have 9 and x squared in the numerator, but only the y to the 4th goes to the denominator. All right, when I look at this, everything now has a perfect square root. So in the numerator, I have the square root of 9x squared, and in the denominator, I have the square root of y to the 4th. All right, well, the square root of 9 is 3. The square root of x squared is just x. And the square root of y to the 4th would be y squared. And this is the simplified final answer for that fraction.